Good morning, and this is my first Google Hangouts video for about 10 months, and I'm sure you've all been eagerly awaiting it. What I want to talk about this morning is using AI to play the game of Pong that you've probably seen from many, many years ago that was originally released by Atari. And this is a very familiar example, and I'm not using my own code. I'll say where it all comes from in the notes afterwards. Here we are. So what we've got here, looking at a live demonstration of the game as trained and fully functional, or more or less fully functional. So let's just remind ourselves of what's happening. The original game, as sold by Atari decades ago, was played on a television screen, and each player would have a control which moved a paddle, the left and right hand rectangles, up and down, and the idea is to prevent the ball from going off your side of the screen. And it was very popular. I can remember playing it as long ago as, oh goodness, about 1980, I think. And they sold lots of these. And recently, if you've been following the AI debate, DeepMind trained on these games and managed to become proficient at all of them, not just this one, but Breakout and numerous others. There's a game called Snake, where a snake runs across the screen. You've probably seen them before. Anyway, why is this interesting? Well, at one level, if you're a human being, you look at the screen and you learn how to manipulate your paddle, and that's all the game consists in. You might think that if you wanted to program a computer to play this game, you would need a complicated algorithm that calculated the position of the ball, the little blue square, and the paddle, and moved the paddle accordingly. And the red square here, that's actually what is happening. The red square always manages to hit the ball because it's being told by the computer where the ball is in terms of coordinates on the screen. But the white paddle, which is what you might call our paddle, isn't being given that information. Instead, the white paddle is being controlled entirely from what you might call looking at the screen. The software takes the screen image, feeds it into an artificial intelligence neural network, in this case structured using TensorFlow, and then the paddle is moved in a way that it gradually learns to move in order to hit the ball. And even now, it does occasionally miss. I think it missed then, in which case its score is reduced by 1. But when it hits the ball and prevents it from hitting the side of the window, its score goes up by 1. And you can see that most of the time it manages to hit it. Now, it's very important to appreciate that this is not being done by the machine being told the position of the ball in absolute coordinate terms and therefore calculating where to put its paddle. That's a possible way of solving the challenge, but it's not the way this solves it. And what makes the approach here interesting is that there are two separate parts to this software. One of them is the neural net that actually tells the paddle where to go. And the other one is the design of the game itself. And in theory, you could replace the game design with any game design, feed the same data into the neural net, and learn to play any game. So the implications of this are very important because it suggests that the computer, by reading screen positions, can derive a behavior that solves a real-world problem in real time. I said that at a conceptual level, human beings literally look at the screen, move the paddle. That's all there is to it. And in a way, this implementation does exactly that for the computer. To repeat, if it was being given a set of instructions based upon knowledge of where the ball was and told to move the paddle in response to that, that would be an algorithmic approach. That would be what we would call a model of how the game works. But that's not how this is done. This is done by a piece of software that takes the screen position, reads it, feeds it into a neural net, as I say, based on a TensorFlow design, which feeds back to it what is in effect an instruction saying move the paddle here or there. If we go back to the game and consider it, you'll see that the paddle doesn't just move at the last minute. It adjusts its position almost as though it were anticipating where the ball would come from, given the position it was in when it returned the ball to the opposition. So let's have a look at that again. That's the red paddle. Now the white paddle hits the ball now, and you can see it goes down slightly, and it waits for the ball in approximately the right position. The ball then goes back. It anticipates that it still needs to be at the bottom of the screen, so it stays at the bottom of the screen. This time, it moves up because it thinks that it's hit the ball in a slightly different way, and the position of the ball on the screen indicates that it's likely to reappear higher up than it was when it was hit. How does it work? Well, it's one thing to make someone else's software run, and that's not altogether easy, believe me, because you have to install all kinds of software before it will run. But even when you have it running, it's interesting to ask how it works. And it's far from simple, but that it works at all is remarkable, and that it works by, in effect, looking at the screen and responding appropriately is the most remarkable thing of all. Good evening. It's dark outside, but if you followed the earlier video about Pong, you will remember that the computer was learning to play just by sampling the screen rather than by giving its explicit instructions or algorithms. Well, this being so, it struck me that it ought to be possible to change the game and have the AI system learn it anyway. So I thought, well, why don't we put an obstacle in the middle of the Pong screen and then see whether it can learn how to play when the ball bounces off the object. It's been playing for about 2 hours, and it's, well, I'm not sure it's doing terribly well, but it's having a go. You can see that there's a green blob in the middle of the screen, just to make it more difficult, and that if the ball hits the blob, it bounces off it. Now, the evil AI on the right with the red paddle is, of course, cheating because it simply follows the vertical coordinate of the ball so that the ball strikes it in the middle of the paddle. On the left, the white paddle is trying to predict the behavior of the ball, but of course it's quite a lot more difficult in as much as there is now a green object that can obstruct the path of the ball and make it go a different way. But if you look carefully, you'll see that there are moments when the white paddle gets it right, such as that, and then the red paddle sends it back, but the white paddle doesn't respond. But there it responded properly to something bouncing off. Here it looks as though it's going to manage. And you can see that its score at 2,565 is really quite respectable, given that it's a game that has just been made up randomly and that there is no strategy. I suspect that by tweaking the way the model is set up, this particular version may need a little bit more by way of memory. It may mean that you have to store more information for the sampling process. And there may be all sorts of other ways that it can be tweaked to make it work better. But it's doing pretty well. It's done about 250,000 iterations at the moment, and it's scoring some points. So that confirms that using image sampling with no explicit instructions as to how the game should be played is tractable. And if you can do it on a fairly old and slow Mac laptop, then obviously you can do it far better on a really fast, powerful machine. My experiment adding an extra obstacle between the two paddles in the Pong game and then expecting the AI to learn how to play it has been remarkably successful. At first, I didn't think it would ever get the hang of it, but it's now done something like 350 iterations, and this is the result. The ball occasionally bounces off the green square, and that obviously adds an extra element of unpredictability to the whole process. But now, after, something like just over 350,000 iterations, the white paddle has got the hang of it. And as far as I can see, I've been watching it for a little while, it's playing more or less perfect Pong. There's the ball bouncing off the obstacle. And the white paddle is having to move quite a long way sometimes to correct, particularly if there is a collision with the green square. Seems to have got into rather a predictable pattern at the moment, but it does eventually alter. There we are. And remember, this has been shown nothing about this game except the screenshots and the score. The score constitutes the reward that reinforcement learning expects, and essentially the search looks for ways to maximize the score by anticipating the right place to put the paddle in order to keep it in play. So it seems that the claims being made for this are true. I'll think about adding extra obstacles and training it again. 350,000 is not that many. And of course, it's running quite slowly on a fairly low-powered computer by modern standards. So we can say that the experiment has been successful. Thank you for watching, and good night. Now, anyone that has ever done any work with computers, particularly in programming, knows that the temptation to say, now I can do that, I wonder if I can do something else, is almost irresistible. This is why one spends so many of one's nights in the small hours sitting in front of a computer screen, scratching one's head and wondering how on earth to make something happen. But after I'd made a single paddle against the evil AI work, and work very well, even with the introduction of an additional complication in the shape of a green square obstacle, I started to ask myself whether it would be possible to make both the paddles respond to the AI instructions instead of just one of them. Because the evil AI isn't very evil, it just always does what it needs to do to hit the ball, but it doesn't have any element of adjustment to what the other paddle is doing. So after a little bit of thought, and I'm sure this is not an optimal solution, but it is a solution, rather than setting up two completely different TensorFlow arrangements, it occurred to me that if both the paddles are, as you might say, engaged in the same task of maximizing the score, given only the data from the screen to read, all one really need do is pass the action variable to the two paddles alternately. Then, simply by reading the data on the screen and aiming to obtain rewards in the form of scores, the learning should still work. And after a bit of fiddling and thinking about it and changing my mind about how to do it, I came up with a scheme where instead of updating both paddles, the system simply passes a toggle to the screen update, which means that the left-hand paddle gets updated and then the right-hand paddle, and so on, alternately. I did think about doing it on the basis of the direction in which the ball was going, but that would obviously then mean that the paddle that the ball was leaving would not do anything until the ball started to come back, whereas it seems to me, just from an observational point of view, that the paddles are adjusting their position all the time in relation to the data they're receiving from the screen about the ball. So that would change the way the game works. Anyway, let's quickly have a look. It hasn't been running for very long, and so I'm quite not expecting it to do anything very exciting, and it's flickering because I think I did something a bit daft in the code, but that can all be dealt with separately. You'll see that at the moment, the white and the red paddles have somehow migrated to the top of the screen. But the red paddle seems to be making some sort of an effort to go down to the bottom so that it hits, so it's gone back up again now, so that it hits the ball. And of course, it hasn't been training for very long. There are 10,000 iterations that don't do anything at the beginning. And so it only really starts the training. The white paddle has just hit the ball there. It only really starts the training from 10,000 onwards. So it's just coming up to 10,000 iterations, which is really nothing in the scheme of things. So we'll leave that running for a while and see what happens. I've often said to pupils, to staff, to anyone who would listen, that in a sense there's no such thing as a failed project. There are only projects that we learn things from we didn't think we would learn. And I've just had a wonderful illustration. In the process of making this or attempting to make this double AI system work, where both paddles are controlled by the AI, I'd obviously made an elementary coding mistake, I think by failing to change something. So I noticed, after it had been training for quite a long time, that when the red paddle on the right-hand side misses the ball, which is a failure, the score is increased. Now, if we were playing a game where the white score increased, that would be fine. But actually, there is only one score, and both the paddles are being driven by the reward system that makes increasing the score their reward for playing the right move. But the fascinating thing about this is that the red paddle had learnt that it got a reward from missing the ball, and in some cases simply moves out of the way. Even though it's in the right position to hit the ball, it, so to speak, knows that it will get a reward if it misses. And so it misses. Let's have a look. Now you can see that the red paddle is in the top right-hand corner, or was. Here we go. And the ball seems to be keeping hitting the object. Now, when the ball hits the red paddle, it doesn't get a score. Let's just have a look and see if we can see that. You see the score does not go up. It might even go down. Does it go down? When it hits the white ball, it goes up by 1. When it misses the red, it goes up by 1. But when it's hit by the red, which I think it's about to be now, it goes down. Or if it doesn't go down, it certainly doesn't go up. What's going to happen here? No, it doesn't get anything because it was hit. But if the red paddle misses the ball, let's see what happens now, the score goes up. And can you see that the red paddle actually moved out of the way? It doesn't do it every time, but then remember, it's still learning. Went down then, down again now, yes. Now it will miss. Red paddle hits this time. And then it deliberately missed it. It moved out of the way instead of moving so that it could hit it. And it did it again there. It went up to 299. Now let's see. It's 300. It hit it, so it didn't go up. That's as a programming error on my part, just not changing a line when I should have done. There it hit it. All seems to be going through the same routine over and over again at the moment, but it doesn't matter for illustrative purposes. There, I think it hit it. It's coming again. Oh, then it's hit that. Now it's going to bounce off. And there it missed, but it got a point anyway. Now, clearly this is not going to work, but it's very interesting in terms of the learning behavior that the screen updating is causing, because the red paddle is doing what it should do. It is behaving in a way that increases the total score. We'll do it again, 291 there, you see. So there's no incentive for it to hit the ball because the reward system is telling it that it will be penalized, or at least it will have no reward if it does. At first, I didn't think that my experiment with the two-paddle AI was going to work. But then I didn't think that the one-paddle AI was going to work either when I introduced the extra green obstacle. I set it running at 4 o'clock in the afternoon, and by 7 o'clock, when it had done something like 250,000 iterations, it wasn't doing very well at all. Considerably later, when it had done something like 700,000 iterations, it was starting to look as though it might be beginning to get the hang of it. So I decided I would just let it run overnight and see where we were in the morning. When I went to sleep, it was looking at a score of minus 1,500. In other words, it had failed more often than it had succeeded in hitting the ball. But it did look as though that might be the minimum score that it would ever get. So I just left it. When I woke up, it had done just under 1.5 million iterations and was looking at a score of about plus 4,000. So let's have a look, and I'll make a few comments about the state that it is in. We still have the green obstacle, which is making life very difficult for it. But you can see that in that example, the red paddle did manage to hit the ball. The white paddle's having a bad day at the moment, but the red is anticipating where the ball will be. White hit it there, red hits it there. And the score, as you can see, is now 6,300, and the iterations 1.6 million. Now, it strikes me that it may be that it will take longer to learn how to cope with the obstacle than it would without it. You'd expect that to be true. Anything that's more difficult to learn takes longer to learn. But you can see from the sequence that we're looking at that most of the time now it is succeeding. Hit. It's going to miss that one, I think. It hits that one. But there's something that needs to be said. This, remember, is a Q-learning algorithm which bases the decisions that it makes now on the discounted total future reward that those decisions will lead to. But basically, when it makes a move, it doesn't just consider winning the next point, it tries to consider winning as many points as possible for the foreseeable future. So it is possible, I'm not claiming that it's true, but it is possible, even likely, that if it misses the ball, it does so because the discounted value of its future successes as a result of missing is greater than the discounted value of its future successes if it hits. This might be, for example, look at what's about to happen there. It didn't manage to hit it. If in moving to hit the ball in one extremity of the screen, it would then miss several opportunities to hit it in another extremity of the screen. There it missed, but here you see it hits. And that is in anticipation of the fact that if it had chased the ball to start with, it would probably have missed the rebound. When the ball doesn't rebound off the green square, the red paddle usually hits it. But if it anticipates that it is going to rebound off the green square, it will sometimes miss it in order to be in the right position to hit several returns of the ball that come after it's bounced. This isn't as daft as you might think. There you see it misses. The white paddle hits. It misses again, but now it bounces off the obstacle and the red paddle is in the right place to hit it. It's again in the right place to hit it. I'm not sure, looking at this, because it's very difficult to tell simply from looking at the screen, whether the ball is in some kind of cyclic behavior and just doing the same sequence over and over again. Perhaps it is, perhaps it isn't. What you can see is that for much of the time, it is succeeding. There it succeeds. There it succeeds. Here, it fails. The red paddle fails. Fooled. The white paddle fails. The white paddle fails. The white paddle fails, and the score reduces, but now it hits it. Now it bounces off. So you can see that although its behavior is ultimately in net terms successful, or the score wouldn't be at plus 6,400, there are sequences during which it misses more often than it hits. And my suspicion is that if we were to leave it, and I will, eventually it might learn how to deal with those as well. But we shall see. Time, as they say, will tell. Conceptually, as I've said earlier in this video, there are essentially two parts to this whole system. There's the game, and there's the AI. At this, from a schematic point of view, it's as shown in the diagram. The game passes information to the AI, and the AI, after doing its magic, passes information back to the game. The three things that the game sends to the AI are the screen, the action, that's whether to move the paddle up or down or leave it where it is, and the score. Does the score equal +1? Does it equal -1? The AI takes this information and considers what it's done in the past. So in other words, associated with this AI as part of its architecture, there is a memory store in which there are a very large number of records of what did I do last time that was a bit like this in this situation. So you have that the AI is, as you might say, comparing the current state of the screen with previous states of the screen, with the action that it took in those previous similar states, and whether it therefore wants to do the same thing or try something different. On the basis of that memory of what it did before, it tells the game what to do this time. The game then simply makes that move, reads the screen again, reads the score again, records the action, and we go round the loop. If we think about the actions, the current game has simply three possible actions. There is stay where you are, there's move up, there's move down. And the game has been assigned these with various probabilities, and they are user controllable. Is that these actions are simply passed to the AI a string of numbers, and in the particular case, for example, where you decide to move up, the second position in the list will be set to 1, and all the others will be 0. All the others will be 0, because there is only one action, and that is move up. When the AI returns the action instruction to the game, it may decide that that's not the right thing to do, and therefore send back a list where something else is set to 1 and the others are 0. Now, there's no reason why the number of actions we consider should be limited to 3. We might consider any number of actions, and those any number of actions might, for example, be move up 1, move up 2, move up any number, or even, although this is just a version of up, jump up, jump down, whatever. Or you could even have an option where you hit the ball. In other words, where the paddle comes in from the side as the ball approaches and actually hits it to send it back. Now, although in terms of the way the game is played, that makes a big difference, in terms of the way the AI functions, it makes no difference at all. The game can have 3 actions, or it can have 1,000 actions, and it makes absolutely no difference to the way this scenario operates. Now, of course, the AI may need a different architecture. The way we're working here, which is a convolutional net with 3 hidden layers and 2 fully connected layers at the end, that might not be the best architecture for this particular game. That's where the skill of the TensorFlow and AI technician comes in as you tune the game. But it doesn't alter fundamentally the concept that only these three things are necessary. Suppose, for example, that the data being shown on the screen is the stock price. The stock price isn't any kind of data at all other than the screen. The data on the screen tells the AI something. The action could be to invest or disinvest, sell in other words, or do nothing, stay. Invest might be considered to be up, disinvest might be considered to be down. And we're really back to exactly the same scenario. The score, well, that might be gain or lose. And gain might be our +1 and lose our -1. On the basis of the screen, we go through here, our AI analyzes this in the light of its previous experience, and it passes back to the game an instruction, which is +1, -1, or 0. Don't do anything. Sell, buy. Let's consider adversarial Pong, where here we have the game, and we have paddle left and paddle right, and alternately, paddle left passes the game information to AI left. Paddle right passes the information to AI right. They both pass action information back to the game. Action for the left paddle and action for the right paddle. So information for the right paddle, information for the left paddle. The screen will be the same in both cases. The action will be different. The score will be different. And therefore you can see that the behavior of the two paddles will be completely separated. When you do this, you can have different parameters for the two paddles. For example, you might operate with a different discount rate left and right. You might operate with a different size of memory. You might operate with different probabilities of assigning the different actions. By fine-tuning these, you could reach a scenario where one paddle beat the other. The scores, of course, would be stored separately. Score left and score right. The outcome you're looking for, if you are this one, is to achieve the scenario where SL is greater than SR. And if you're this one, you're trying to have SR greater than SL. You could, in addition, instead of having negative scores when the ball hits the side of the screen rather than the paddle, you could obviously have the way it's normally done in video games, which is to have a number of lives for each paddle, and it would lose a life when it hit the side of the screen, as well as losing a point. Once you have two different AIs, then you can set them up differently. When you have a system in which two paddles are competing with one another as controlled by two different AIs, one for the left paddle and one for the right paddle, the two AIs need not be set up the same way. For example, in the game that we are running, we're operating with a discount rate of 99%. But you might wonder whether that's actually the right discount rate. Couldn't you operate one with a discount rate of 99%, one perhaps with a discount rate of 90%? One AI might be operating with 500,000 slots in its memory list. The other one, we might say, well, let's give it 1 million. This one might be pooling in accordance with a particular stride and kernel pattern. Why not make this one different so that it's looking at the screen and sampling the screen in a different way? What this then suggests is perhaps the most intriguing possibility of all, which is that the two AIs might be conceived as in competition, rather like the left and right paddles. So that you might have a third AI, a meta AI, looking not at the game, but at the AIs, and receiving from each AI the parameters, that's the values that we were just talking about, the discount, the memory, the pooling, and any other parameters that are set inside the AI, receive the AI's parameters from each of the AIs, consider which of the AIs is performing better. In other words, for example, which of them has scored the most. That might be a feed from the game. And then suggesting to each AI that it might operate with revised parameters for the next move. The meta AI is then changing the configuration of the left and right AI, which will in their turn, therefore, make different suggestions to the game about which actions to take. The idea of an AI controlling an AI also suggests that in a suitably sophisticated scenario, the architecture of AIs might also be redesigned by another AI that would say, well, you have 3 hidden layers, 2 fully connected layers, this pooling operation, this convolutional configuration. Let's change that. So you could have a meta AI that not only tinkered with parameters, but actually tinkered with the fundamental architecture of the neural net. If you're not excited by this, you should be. Because the generality of this scheme, the fact that it is a game, so-called, doesn't make it trivial. Any decision process can be conceived as a game, and almost all games, including the game of life itself, are linear in the sense that you make actions one after another. Those actions maybe lead to a positive score, or they may lead to a negative score, success or failure. But to go back to the point I was making about the Pong, whether this is the right move, in other words, whether to hit the ball now produces the greatest long-term discounted benefit, not the same question as whether you should hit the ball now just to win a point now. It's perfectly possible that losing a point now is the optimal strategy when you consider your score in the long term. We're up to 1,660,000 iterations. I'm assuming that it's still learning. I don't have enough output parameters really to show me that very easily. But what you can say is that it's now got a score of 6,822. And it appears to be hitting the ball more often than not. And that example we just saw is very interesting, where the red paddle didn't attempt, so to speak, to hit the ball because it knew that it was going to bounce off the obstacle and that it needed therefore to be in the upper position in order to defend that result. Now it thinks it isn't going to bounce off the obstacle, so it heads south. The white paddle missed, but it's not going to miss this time. The red paddle isn't going to miss this time, but it actually can manage the bounce too. And I suspect that this is still learning and getting better. in another few hours, we may be in a position to decide that definitively. The game has now been running for a little bit less than 24 hours and has just hit, or is about to hit, 2 million iterations with a score in excess of 12,000. So the game has learnt to play. So we can see that the number of iterations has just passed 1,999,000, that the score is just over 12,500. The ball seems to be following a rather predictable and indeed monotonous course at the moment, so perhaps it's settled down and is not going to change anymore. But just occasionally it hits the obstacle, and on this occasion, as you will have seen, the red paddle was ready for it and hit it. And the game seems, therefore, to have improved enormously over the course of this long training period, and we've just topped 2 million with the score at 12,558. So this is a proof of concept that even if you add extra features to this system, like the green square, or such as having both the paddles controlled by the AI, and remember in this case they're both being controlled by the same AI system, even so the system still learns and still produces very good outcomes, albeit over a very long period of time.